welcome to ICU Primary Prepcast.
Hi, I'm Maddie.
Hi, I'm Swapnil, and welcome to our 99th episode of ICU Primary Prepcast, which is very exciting. It's been a while since we recorded the last episode, and obviously there was a lot of things going on in everybody's life, so we got kind of distracted with a few things. But here we are, back on track. So, Maddie, how's things been with you, and what's happening?
Yeah, pretty good. Busy. I was saying before we started recording, but we've just had winter, like a constant stream of illnesses secondary to a toddler. So his immune system's amazing and he just bounces back. But we've been like under the weather a lot. So like the perils of getting old.
Yeah, look, I think the ICU has been quite busy but we are back on track, and this is our 99th episode, which is also quite amazing. So, Maddie, we are going to start something which can be a quite favorite topic for a lot of intensivists. And we do see these patients often in intensive care unit where struggle with fever of unknown origin. But real question is, how do we measure temperature? How we define fever? And what are the kind of different modalities that we use to measure temperature? But before we dive into temperature measurement, can you please define some of the key terminologies like heat, temperature, and specific heat capacity?
Yeah, so I thought this was interesting because it's something that we kind of assume as like we know what it is, but when you try and define it, it's actually a big struggle. And a lot of different books and websites and everything define it differently. So these are the ones that I got from one of the textbook about, like, I think it's like physics or something for the anaesthetist in intensive care. So they define heat as the transfer of energy between objects of differing temperatures, and temperature as the intrinsic physical property of a substance that's related to the kinetic energy of the molecules within the substance, and specific heat capacity as the thermal energy required to increase the temperature of 1 kilogram of substance by 1 Kelvin without changing its state of matter. And I think none of these are very intuitive definitions, so it's probably something you just have to look up and memorize.
The beauty of this question, when I kind of reframed it, the only 10% marks allocated to 3 definitions. So even if you kind of know 1 or 2 definitions, or you're likely to get at least half a mark or 1 mark. So there is not a lot of weightage to the definitions. So don't panic if you don't know the definitions. But even if you write 1 or 2 definitions, you are still likely to get marks. So the weightage is not that much. So yeah, you're right. There's not many textbooks will have these answers catered for you. So you have to do a little bit of search around it. Now, the next question is going to be really what we think as examiner is a bread and butter question for candidates. And in intensive care, we all should know about this because we do it every single day. Having said that, again, there is an assumption built in because we only use 1 or 2 modalities to measure the temperature. So can you please outline the principles underlying the different methods of temperature measurements? And just to simplify, you can classify them into electrical methods and non-electrical methods.
Sure. So the major principles, if you look at the show notes here, I've put more details in it in sort of a table form, dividing into non-electrical and electrical methods. For non-electrical methods, the major principle outlining the majority of the different modalities is something called thermal expansion. This is where a liquid or a gas expands with increased temperature and contracts when cooled, and it's then coupled with something or calibrated against a temperature measuring scale. So examples of these include liquid thermometers. So these are like the classic thermometers you might remember from your childhood, which are have a liquid such as alcohol or mercury, which expands with increased temperature and then contracts when cooled. And this liquid is placed in a thin walled glass tube, and the change in the volume of liquid causes the fluid level to rise or fall in the tube alongside a calibrated scale. So then the temperature is based on, or read based on the height of the column. And this is pretty cheap, reusable, easy to use. It's readily available. It doesn't require any external battery or power source. It's fragile, as it's usually in a glass tube. It can have toxic elements such as mercury. And because the cylinder of glass is needed to magnify the column of fluid, it increases the measurement error. The same principle is used for other non-electrical methods, such as the Bourdon gauge or the bimetallic strip methods. So the Bourdon gauge also uses thermal expansion. It has a temperature sensing bulb which contains a fluid or gas, and this expands when the temperature increases. But the coupling mechanism is a hollow spiral metal tube which then unwinds with this change in volume, and it moves a pointer on a calibrated scale. And similarly, a bimetallic strip also uses thermal expansion, but instead of using a fluid or a gas, it has two different metal strips which have different coefficients of thermal expansion, and they are connected along their lengths. But these metals change at different rates for the same temperature. So one side expands while the other does not. And so when the temperature rises, the strip will turn towards the metal with the lower temperature coefficient, and the deflection of the strip indicates the temperature variation. And so this bending of the metals is connected to a dial, which is calibrated to a temperature scale. All of these methods are usually quite cheap, not requiring external power supports, but they generally have the same sort of fallibility in that they have a slower response time, and some of them require frequent calibration. The other non-electrical method that's used is a liquid crystal thermometers, which uses something called thermochromism, where a color changes in response to a change in temperature, which is again used against a calibrated scale. And then finally, the electrical methods. So these have a few different kind of principles underlying them. One of the major methods is something called a thermistor, where a resistance of a metal oxide changes in an exponential manner to a change in temperature. And the thermometers are generally negative temperature coefficient thermistors, so the resistance decreases as the temperature increases. These are like quite useful because they're small, they're robust. They're used in things like pulmonary artery catheters or nasopharyngeal temperature probes, so things that we see often within the ICU. They're sensitive and have a fast response time and are cost effective, but they do require calibration. Then there's something called a resistance thermometer, which uses a similar principle, but they use a metal where the resistance increases in a linear manner as the temperature increases. And this is often through a pure metal such as a platinum wire. This is more accurate over a larger range of temperatures, and it's not prone to drift, but it's more expensive, so often used more in like a lab setting. And then there's the thermocouple, which uses something called the Seebeck effect, where a temperature difference between two similar metals creates a voltage, which is directly proportional to the temperature. This, again, is accurate with a rapid response time and can measure a wide range of temperature, but only a small voltage is generated by this difference in temperature, so it needs signal amplification. And then finally, there are infrared thermometers, and these are something that they're the ones you might think of, like if you put one in someone's ear on their forehead, they measure the surface temperature. So they use something called the Stefan-Boltzmann law, which states that every piece of matter not at absolute zero will radiate thermal energy proportional to the fourth power of its absolute temperature. So the temperature can then be calculated from the intensity of the infrared wavelength that's emitted, or the radiation that's emitted from the source. So this is generally non-contact kind of thermometers, and they're fast, but again, they only measure the surface temperature. So, for example, the ear ones, if your ear is obstructed by wax, it'll give you a very inaccurate temperature. And people like in the ICU setting, where often we want to measure core temperatures, they might not be as accurate.
Thanks, Maddie. So that's a very comprehensive answer. Now, this question has troubled a lot of candidates because I think we often don't pay much attention to how exactly the temperature measured in ICU and what techniques do we use. But also some of the techniques are old, like as you said, the mercury thermometers, that they're not anymore in the use. A lot of candidates read about the physiology of temperature, but then also reading about the measurements and physics is quite important to pass the question and why what. So
I think if you think of any sort of like big pieces of equipment we use in ICU, and to have some understanding of how they work for the primary is really important, and for your career. But, this is geared towards exam.
That's right. Thanks, Maddie. So that's the end of our today's snippet. We'll be back with another snippet soon, which will be quite exciting because that will be our 100th episode of primary. So stay tuned. And I'm pretty sure we will celebrate it with the bang at the end. So stay tuned.
Thanks for listening. See you next time.
See you next time.